actually start to talk about the course content today. I briefly touched yesterday on what is a rational expression, and I want to make sure that we just review that today. And then we're going to start to talk about what these are all about. Okay, so from yesterday, who remembers? You may not have written this down, but we did look into what is a rational expression. What's that? Yes, it's an algebraic fraction. Okay, so oh no. This thing was acting up today. Okay, there we go. Is a fraction with algebra in it. And specifically, the numerator and denominator have to be a specific type of algebraic expression. Yes? Right. So the numerator and denominator are polynomials. Okay? So that is what a rational expression is. And we looked at some examples yesterday. I know this was just sort of a tangent that I went on, so you guys may not have written them down, but something like x squared plus 3x plus 5 over x minus 2. That would be an example of a rational expression. Okay? Now, what we are going to learn to do in this unit with these expressions is what you guys learned to do basically when you started looking at fractions. So you learned to simplify them or reduce them. You learned to add, subtract, multiply, divide them. Okay, so we're going to do that. And you also, well, you may have, I'm not sure about this, but you may have solved like a linear equation that might have involved a fraction in them as well. So we're going to do that too. We're going to solve equations that involve these expressions. Okay, but essentially you're just relearning all the stuff that you know about fractions now with algebraic expressions instead. Okay, for today and tomorrow, really all that we're going to focus on is this simplification process and also figuring out if two rational expressions are equivalent or not. Okay, so what I want to just remind you of is how you did that with fractions. Okay, and why perhaps two fractions are equivalent to one another. How do we reduce fractions? How do we tell if they're equivalent? That sort of thing. Okay, so I'm going to take three fractions. Let's say I have 12 over 18. 24 over 32. And, okay, I'm just making this up on the spot. 60 over 90. Okay, so are any of these rational numbers reduced or simplified? No, none of them are, right? We can simplify them all. So let's say you wanted to simplify 12 over 18. How did you, what would that become? 12 over 18, yeah. So 6 over 9 is sort of partially simplified, yes, yeah. 2 over 3, okay? Now, what you probably learned to do when you were back in elementary school is kind of do it in your head, or maybe make a list of factors of 12 and factors of 18, and then cancel out the biggest common one, something like that. But what I want to show you, actually, is that you can simplify these things using prime factorization. because that is the analogous process that we are going to have to use when we simplify rational expressions. Okay, so let's say I look at 12. 12, you can break that down into 4 times 3. And then 4 you can break down to 2 times 2. So 12 is 2 times 2 times 3. Does that make sense? 2 times 2 is 4. 4 times 3 is 12. Over 18 is 2 times 9, and 9 is 3 times 3. So that's 2 times 3 times 3. Or you can think about 2 times 3 is 6, 6 times 3 is 9. Okay? Now, what we can do once these two numbers have been prime factorized is cancel common factors. So there's one factor of 2 that they have in common, because 2 divided by 2 is just 1. So essentially that part reduces to 1. And then we can also cancel a factor of 3. They both have a factor of 3. And what we're left with is 2/3. Okay, and this works every single time. Okay, 24 over 32. Now, with some of these, you may have to think about prime factorization like off to the side, right? And with numbers, if you just know what that reduces to, I wouldn't recommend using prime factorization, because you should be using the most efficient thing that comes to mind. And oftentimes, because you guys have been doing this for so long, you may just know how a fraction reduces. But really the reason I want to sort of get into the weeds here is because we do need to break this down into individual factors when we do this with rational expressions. Okay? So if we think about 24, that would be 2 times 12. 12 is 2 times 6. This is 2 times 3. Okay, so this is going to be, in the numerator, 3 2s and a 3. Okay, 32 is 2 times 16, 2 times 8, 2 times 4, 2 times 2. Yes? So far, so good? Okay, so that's 1, 2, 3, 4, 5 2s. Okay? So again, we can cancel common factors here. We've got 1 factor of 2 that cancels, 2 factors of 2, 3 factors of 2. And what we're left with in the numerator is 3. In the denominator, we have 2 times 2, which is 4. Okay? And then 60 and 90, I really didn't leave myself a lot of space. I'll have to do this maybe up here, the prime factorizations of those. So 60 is 2 times 30. My process for prime factorization is I start with 2's and exhaust that as much as I can. And then I try 3 and see if that works, and I exhaust that, etc. Okay? This is 2 times 15, and then 15 is 3 times 5. Okay, and then 90 is 2 times 45. Now, 2 doesn't work anymore for 45, but 3 works. I can write that as 3 times 15, and then 3 times 5. So 60 is 2 times 2 times 3 times 5. And 90 is 2 times 3 times 3 times 5. Okay, and then when I look at the common factors, I've got a common factor of 2. And then there's no other 2 in the denominator, so I can't do anything there. Common factor of 3, common factor of 5. And this works out to be 2/3. Okay, which of these original fractions are equivalent? The 60 over 90 and 12 over 18. Yeah, okay. So how could we tell? Well, we simplified them both. And when we simplified or reduced them both, we got the same fraction. Okay? This is kind of the process that we're going to do with rational expressions. So we're going to break the numerator and denominator down into the smallest of factors, which is why we reviewed factoring yesterday. And we're going to see if any of the factors cancel. And then if we want to see maybe is this equal to another rational expression, we'd have to do that for both and see, okay, well, what do we get once they're fully simplified? Do we get the same expression? And if we do, then they would be equivalent. Okay, so that's really what we're going to be doing for the first piece of this before we start to look at add, subtract, multiply, divide. Okay, now there is one caveat with these rational expressions. Okay, when we looked at the definition of a rational number, I kind of glossed over this, but the definition of a rational number is that you have to be able to write it as a over b, but b can't be 0. So you can't divide by 0. Do you guys know why? You may remember being told that. Do you know why? Yeah. It's not going to, okay, so that you think maybe exponents. It doesn't work is true, yes. Do you have an idea? Yeah.
It then becomes like undefined. So
Yep, it is undefined. Lachlan? Okay, so I do want to kind of talk about this a little bit. We can't divide by 0. We get an undefined value. Now, there are sort of three explanations that I go into as to why this is the case. One of them I use for like really little kids, which is like, okay, so you have 5 cookies and you have to divvy them up to 0 people. How do you do that? You can't. Because the cookies have to go somewhere, but they have nowhere to go. Okay? So that's one explanation. The explanation that I'm really going to use with you guys is to think of the fact that multiplication and division are opposite processes. So for example, think about this. 3 times 5 equals 15. If this statement is true, then there has to be 2 division statements that are also true. So the division statements that will come out of this is that 15 divided by 3 equals 5, and also 15 divided by 5 equals 3. Okay, are we all okay with that? Okay, so let's suppose that you had 15 divided by 0, and that actually equaled some number. We don't know what it is, but suppose there is some number that exists where you go 15 divided by 0, and that's what you get. So if this is true, then the associated multiplication statement would also have to be true, which is that that number times 0 would have to equal 15. If that number existed, then this would also be true. Okay? This is not true, because whenever you take any number and you multiply it by 0, you get 0. You don't get 15. So this is impossible. So what we conclude from that is that if that's impossible, this number doesn't exist. Or it's undefined. We have no way of defining it. Okay? Questions with that? All right. So let's talk about non-permissible values. If we have a rational expression, let's say 3x over x minus 5. Okay, this will have a different value depending on the value of x. So for example, if x equals 1, this would be 3 over 1 minus 5, 3 over negative 4. Right? If x equals 0, this will be 0 over negative 5, which is 0. Okay? But there is one value of x that would make this expression undefined. Yes?
Positive
5, yes. x equals 5, if x equals 5, this expression is now undefined. Because if x equals 5, I'm going to have 15 divided by 0. I didn't intend to do that, or 15 divided by, that's a good, okay, cool. That's just total random luck. Okay, but yeah, I'm going to have that if x equals 0, I'm going to have 15 over 0, and that's undefined. Okay? 5, therefore, is called a non-permissible value. It's a non-permissible value of the variable because when x equals 5, the entire expression is undefined. Okay? So here, x cannot equal 5 since that would make the denominator zero. Okay? And when the denominator is equal to 0, we have an undefined expression. So in general, a non-permissible value, or you can call it an NPV, are any values of the variable that make the expression undefined. Okay? Well, what that means is that the denominator is 0. Okay? So, I can't remember if I put examples on the next page, did I? Yes. Determine the non-permissible values for each expression and explain why or why not they exist, or why why they do or do not exist. Okay, so when you are looking for non-permissible values, we need to focus in on the denominator and say what value of the denominator would make this denominator equal to 0. Okay? Sometimes there are values, sometimes there are not. Okay? So let's take a look at this guy. What value of x would make the denominator equal 0? It's kind of a trick question. What's that? Say that again? Well, we have x minus 3 over 23. What value of x makes 23 equal to 0? If x is 3, we'd have 3 minus 3 is 0 over 23. Is that defined? 0 divided by 23 is 0. Take nothing, divide it into 23 parts, you still have nothing. Okay? This doesn't have any non-permissible values because the denominator is 23. Doesn't depend on x. Okay? So there's no value of x that will ever make the denominator anything other than 23. So this example has no NPVs because the denominator will always be 23, which is not 0. Okay? What about the second one where we have the reciprocal, 23 over x minus 3? Yeah.
NPV is 3?
Right. The non-permissible value here would be 3 because 3 minus 3 is 0. Okay. Now, I want to actually do D first and then go back to C. Okay, so for D, we have this expression 2x plus 1 over x squared minus 4. So what value of x would make this 0? Yes.
2, because 2 squared is 4.
Yes.
If
So
you subtract 4 from 4 equals 0.
correct. So 2 is one of them. But there's 2. Yeah.
Negative 2?
Correct. So this is 2 and negative 2. 2 squared equals 4. So 2 squared minus 4 is 0. Negative 2 times negative 2 is also 4. Okay? Now, how do you figure that out? The easiest way to do this is actually to make sure that before you state your non-permissible values, you completely factor the denominator. Okay? So if we factor this, then we can't really do anything in the numerator. There's no greatest common factor here. This is not a difference of squares. But we can factor the denominator. How would that factor? Yeah?
X minus 2, x plus 2.
Right. X plus 2 times x minus 2. Okay? Now, every unique factor in the denominator will produce a non-permissible value. What I mean by unique is that if they're different. If I had like 2 factors of x plus 2, you're just going to get one non-permissible out of there. But as long as the factors are different, they will each give you a non-permissible value. So here, x cannot equal 2 because 2 minus 2 is 0. Here, x cannot equal negative 2 because negative 2 plus 2 is 0. Okay, make sense? When you are solving a problem that involves rational expressions or equations, the expectation is that somewhere along the way, you state the non-permissible values. So this is something that needs to be done every single time. And just to foreshadow a little bit, pretty much every single question that we're going to do is going to involve factoring. Okay? All right, let's look at this guy. 2x plus 1 over x squared plus 1. Okay. Well, is there anything that we can factor here? No, this is a sum of squares, okay? Now, to be honest, just because you can't factor it doesn't necessarily mean that there's no non-permissible values. You won't see that in this course, but if you remember back to last year, you looked at the quadratic equation, where you have irrational values that make the denominator equal 0. Okay, so I'm not going to say that if it's not factorable that there's no non-permissible values, but you're not going to see that in this course. But if we think about this, if you just look at x squared, if you take a number and you square it, think about the sign of that. So I mean like positive versus negative. Take a number and square it. What's the sign of a number squared? Yeah. Positive. Unless it's 0 and then it's 0, right? But this will always be positive. If you take a positive number or 0 and then you add 1, what are you going to get? Positive number. So because of this specific expression, positive number or 0 or bigger plus 1 is always going to be positive. So this also will never be 0. So this has no non-permissible values. There is no value of x that would make that expression equal to 0. Okay? You can also think about, like, let's say that x squared plus 1 did equal 0. Then x squared would have to equal negative 1. That's impossible. Because a number times itself will always be positive. Okay? So in general, how do we solve these problems? Well, look at focusing on the denominator. If you can factor it, factor it. If you can't, then just focus in on the denominator that you have and ask the question, what value of x will make this 0. Okay? All right. Here's some questions for you guys to try. Okay, so demonstrate by substitution. So we have to take this expression, okay, and sub in a -2. So 2 times -2 over -2 squared plus 2 times -2. Okay. I recommend that whenever you substitute, you replace the x's with a set of brackets like I've done. And it's especially important when you're substituting in a negative value, okay? Because -2 in brackets squared is +4. -2 squared is actually -4 if this wasn't in brackets. And if you are trying to do this on your calculator, you're going to be confused, okay? So when we evaluate this, 2 times -2 is -4. -2 all squared is -2 times -2. That's 4 plus 2 times -2 is -4. Okay? And that is -4 over 0. And this is undefined. Therefore, have you guys ever seen this before? Yeah, those 3 dots, that means therefore, often used in math, science, all sorts of things. Therefore, x cannot equal -2. Okay, so just make sure, really important, that you pay attention to the directions. If you're asked to determine the non-permissible values, then you'd have to factor this, right? If you're asked to demonstrate by substitution, you need to substitute in. Okay? All right, so I want you guys to try these 2. And then we'll talk about simplifying these things. So we're going to start to talk about simplifying rationals today as well. I already sort of mentioned what simplest form means, right? So with numbers, when we're talking about simplest form, okay, when we're talking about simplest form, if we have, I'm just going to use one of the examples we already did. 12 over 18 is 2 times 2 times 3 over 2 times 3 times 3. And simplest form is essentially when you find an equivalent rational number where there are no common factors in the numerator and denominator. Okay? So simplest form is an equivalent fraction with no common factors. I should say other than 1, right? 1 is a common factor in the numerator or denominator. Okay? Rational expressions work very, very similarly, except we have to consider non-permissible values, okay? With rational expressions, it's the same as numbers, but we also need to consider non-permissible permissible values. Okay, so for example, let's say we have this rational expression here. 4x minus 7 times x plus 3 over 2x minus 14. Okay? Now, whenever you're doing anything with rational expressions, almost, I would say 99.9% of the time, the first thing that you want to do is factor everything that you can. Okay? So when I look at the numerator, that has already been factored. And in fact, in this course, if one of the polynomials happens to be a trinomial when it's expanded, it will always be given to you in factored form like this one is. Okay, so that piece is done. Can we factor the denominator? Yes. Okay, so what can we do with the denominator? Right. There is a common factor of 2. And we're left with x minus 7. Okay? So here's what we're going to do. Step 1 to all of these questions, factor everything. Okay? Step 2. What do you think we're going to do next? Say that again?
Me?
Yeah.
Oh, cancel out the values on the.
Okay. So that's so tempting, and we're going to do that eventually. Very soon, actually. But actually, what I recommend doing right now is stating your non-permissibles. Okay? Because if we just cancel that x minus 7 out, it almost looks like it was never there to begin with. And it actually was. The only way that our simplified expression is going to be equivalent to this one is if it has the same non-permissibles. So step 2, state NPVs. Okay? So in this case, I'm just going to write on there x cannot equal 7 because I'm only focusing in on the denominator. Okay? Now we can cancel common factors. Okay? So I can cancel this. Is there anything else I can cancel? Yeah, 4 over 2 equals 2. So this simplifies to 2. And so what's left is 2 times x plus 3. Okay? And as long as we write down that x cannot equal 7, these two expressions are equivalent to one another. If we don't have this down, they're actually not equivalent because the original has a non-permissible and this one wouldn't. Okay, so really important that you include that in there. Okay, let's try another one. Simplify this rational expression. Okay, well, this is a monomial over a monomial. So there's actually nothing to factor here. We just want to cancel any common factors between the numbers, between the a's, and between the b's. Now, some people do actually find it helpful to expand the factors. So instead of writing 15a squared b cubed, you would write 3 times 5 times a times b times b times b over whatever the denominator is. So you can do that if you want, if it helps, or you can just think about your exponent laws. Okay, so I'll show you how to do it both ways. When I'm simplifying this, if I'm just thinking in terms of my exponent laws, I'm going to set up my fraction. I'm going to think, okay, 15 over 30, that simplifies to 1/2. Right? A squared over a cubed, there's 2 factors here and 3 factors here. How many will cancel? 2. Where's the remaining one going to go? Denominator. Yeah. No, that's a, right. Okay, and then for the b's, there's 3 factors here and 1 there. How many are going to cancel? 1, and there's where are the 2 left over? In the numerator. Okay, so you can think about it that way. If you're struggling to see that, what you may want to do is sort of, I'm going to use quote unquote prime factorization, because we can prime factorize the 15 into 3 times 5, and then we're not factoring this per se, but we're writing it in expanded form. And in fact, we did this when we were working with logarithms and our exponent laws. So we've seen this before. 30 is 2 times 15, so 2 times 3 times 5, a times a times a times b, right? And then you can do this. So if you look at what's left in the numerator, it's just b times b, which is b squared. And in the denominator, 2 times a. Right? That's the same as 1b squared over 2a. Okay, so either way, when you have that monomial over monomial, you want to just think in terms of your exponent laws. If you have anything else more than 2 terms, you have to think factoring. Okay, let's look at this guy. 2x minus 6 over 9 minus 3x. So we want to simplify this and state all restrictions on the variable. All right, so numerator and denominator, can they be factored? Yes. Okay, so in the numerator, how can I factor that?
2.
Greatest common factor of 2. Yeah. So I take out a 2, and what's left? 2x divided by 2 is x. 6 divided by 2 is 3. Okay, and then in the denominator, I can take out a 3, and I'm left with 3 times 3 is 9. 3 times x is 3x, so minus x. Okay, so factored. That's good. What are the non-permissibles here? 3, right? Because 3 minus 3 is 0. So x cannot equal 3. Okay, are there any factors that I can cancel? Yes, no, maybe? Yeah?
On the bottom, you can take out -3 instead of just regular 3.
Right. Yes. So this comes up a lot in this course, I've noticed, like on diploma exams, that kind of thing, where you have 2 binomial factors that are identical except that their subtraction in the order of the terms is reversed. Okay? So when you see that, there's 2 ways to go about it. One way, and this is mathematically what's going on, is to write this with the same numerator, but instead of factoring out a 3, I'm actually going to factor out a negative sign as well. -3 times, think about this, -3 times what is 9? -3. And -3 times what is -3x? Positive x. Okay? Now these factors are identical because they have the same terms and the same sign in front of each term. Okay? So now we can cancel this. And this is equal to 2 over -3 or -2/3. Okay? Now, the shortcut is this. The shortcut, and honestly, if you remember this, that's great. But if you start making mistakes, then I'm going to be like, no, you got to go back to factoring out a negative sign, is this. If you can kind of establish, okay, let's say I have 10 minus 2 over 2 minus 10, right? So I'm just giving numerical examples where we do this thing where we flip the order of the terms, or let's say 1 minus 5 over 5 minus 1, right? Oh, not 10, 1. Okay, so this kind of looks similar to the situation that we had. This is 8 over -8, which is -1. This is -4 over 4, which is also -1. Okay, so this always happens. So if you have this, a over b, or a minus b rather, over b minus a, okay, it doesn't cancel to make 1, but it does cancel to make -1. So this equals -1. So an alternate thing that you could do instead of factoring out the -3, and honestly, I don't care what approach you take, is if you have this 2 times x minus 3 over 3 times 3 minus x, okay? You can cancel this as long as you multiply the whole thing by -1. Because something minus something over like the reverse, like these situations, A minus B over B minus A will always equal -1. Okay, so altogether, -1 times 2/3 is -2/3. Okay, so you can pick whichever strategy you like, and I'm fine with either. My hesitation, I suppose, is that people forget that it equals -1 and they just cancel it, right? So you have to make sure that you're paying attention to that, especially on things like multiple choice questions where it's either right or wrong, right? There's no sort of forgiveness or leniency in those questions. Okay, so I want you for the rest of class to practice these questions. You have to simplify and state the non-permissible values, and then we're going to pick this up tomorrow.